for the rest of the quarter. I think Shant back there is in charge of the video. If you do not want the back of your head videoed for any reason, then move to the back of the class. You know, as I mentioned in discussion section yesterday, I totally honor you for going up in front of the class and presenting problems. So you can imagine how terrified I am to have myself on video that will probably eventually be on YouTube. Okay, so okay, so I want to start off by continuing where we left off. We're starting on our next lecture on molecular orbitals. And remember lecture 1, that was more than a 1-hour lecture. We talked about the fundamental idea behind arrow pushing, that it represents the interaction of filled orbitals with unfilled orbitals. And I gave you 7 rules for mechanistic arrow pushing that we are going to agree to follow as a class when we do problem sets, when we do exams. Those are the times when you really have to pay attention to those rules. And so because arrow pushing represents the interaction of filled orbitals with unfilled orbitals, we have to make sure we all are on the same page with orbitals. So today we're going to talk about orbitals. And I want to start off with a simple problem for you to solve. Let's just imagine that we have 2 particles that are both positively charged on the atomic scale. And to make things meaningful, let's make these 2 protons that are ready to form a bond. And we all understand what electrostatics does. We understand Coulomb's law. If you were an electron with a negative charge, what's the ideal position for you to occupy relative to these 2 positive charges? An electron has a negative charge. I think we have this idea, I have this notion that I want to put that negatively charged electron right there. With all of my being, I want to put that electron there. But if you do that, you have violated the Heisenberg uncertainty principle. You can't specify the location of an electron. You have to put that electron all over the place. And that's what results in bonding. So we have 2 simple outcomes to that. One is we need orbitals. We need some sort of mathematical description of the probability of finding an electron smeared all over the place around those 2 hydrogen atom nuclei. So there's a second problem here. Whenever we put electrons into orbitals, we put them in 2 at a time. We put in electron pairs. And because we're putting in electron pairs, we need some way to show that those electrons will avoid each other. And so as a result of that, we need phasing. We need to phase those orbitals to show that there's a way for the electrons to get out of the way. And so let's go ahead and draw the canonical types of orbitals that we will use in this class. And there's really only 2 types. I'm going to represent an s orbital like this as just simple little balls, and they'll have phasing, either hashed phasing or unhashed phasing like this. We'll also use p orbitals. And we'll represent them with this kind of lame representation like this. They don't look exactly like that, but this is good enough. And they could have various orientations with the x or y or z axes. So these are p orbitals. And so note the importance of phasing. Here I've separated the two different s orbitals. You have to imagine them on top of each other with that different phasing. Okay, so phasing allows us to think about the idea of having 2 electrons around the same place in space but avoiding each other. And so we need that. Okay, so we're going to talk about 3 types of orbitals today. And it's supposed to be review for you. Supposedly these are ideas that you've already seen before. And so the intention is to review. So first we're going to review atomic orbitals. This is the stuff that you know as s, p, d, and f orbitals relative to the structure of atoms. Then we're going to talk about combining those things into hybrid atomic orbitals. That's sp2, sp3, sp, stuff like that. So you should be familiar with that. And then finally we're going to talk about combining those things to make molecular orbitals. Okay, so let's go ahead and start off with atomic orbitals. Hopefully we can add some new insight. Hopefully you can take these ideas that I'm sure you heard at some point in time, but when you take those ideas and you reapply them to reactions you already know, then hopefully you'll be able to do some more stuff with that. Okay, so let's go ahead and start off with atomic orbitals. So there's 4 types of canonical atomic orbitals that we use in chemistry commonly. There are potentially other shapes and other formulations, but these are the ones that you should be familiar with from freshman chemistry and from sophomore organic chemistry, from general chemistry and organic chemistry, and that's S, P, D, and F. Now, fortunately, we can rationalize everything in this class with just S and P orbitals. Now, there will be examples of organometallic chemistry, transition metal chemistry, where we will need to put in D and F orbitals, but we will be able to explain everything in this class just by focusing on S and P orbitals. In a way, that makes our life incredibly simple, but what you'll learn is just handling these 2 types of orbitals and the way they interact is going to be immensely complex and yet immensely powerful. Okay, so we're just going to focus on S and P orbitals in this class, and I have one super important statement to make. And that is that p orbitals are higher in energy than s orbitals. I think every one of you knows this already. But what you don't know is just how powerful that is. And so let me go ahead and start off by graphically representing the fact that p orbitals are higher in energy than s orbitals. And I'm going to start by using a construct that we're going to use many times in this class called a molecular orbital or an orbital energy diagram. I'm going to have some mystical orbital axis here, and I'll call that E. Sometimes I'll write E with a subscript like MO for molecular orbitals. Or maybe I'll just write here orbital. And I'm going to show you some atomic orbitals. So let's graphically represent the fact that p orbitals are higher in energy than s orbitals. And I want to focus on p orbitals on a carbon atom. Because this is organic chemistry, we care most about carbon. Usually everything that I talk about is going to be carbon or else nitrogen, oxygen, and then sometimes things from slightly lower levels. So this is a p orbital energy. There's 3 types of p orbitals. They're orthogonal to each other. If I draw the shapes out for those orbitals, and I'm going to draw a little subscript here on that p to tell me that I'm talking about a p orbital on carbon. You'll see why that's important that I specify that in just a moment. So let me go ahead and try to represent those p orbitals. This would be a p orbital aligned with the y-axis. And there's 2 other orthogonal types of p orbitals that can coexist in space on a carbon atom. These are the other types of atomic orbitals. There would be one on the x-axis. And I'm showing one of 2 arbitrary phasing combinations here. And then finally, there's one sticking straight out at you that would look something like this. And I'll try to draw the hashed part going in back of the plane of the board. Okay, so those are p orbitals. The important point is that these are way higher in energy than an s orbital on carbon. And I'll put a subscript there. Vastly higher in energy. If you were an electron in a p orbital, you'd be much more energetic and likely to attack things than an electron in an s orbital. That's the importance of energy, and that's what you care about. You care about which electrons are likely to attack other things. It's the most energetic ones. Conversely, if I were a pair of electrons and wanted to put myself somewhere, I would want to go into the s orbital because it's lower in energy. Electrons always want to go into orbitals that are lower in energy. That makes sense. They're more stable. That's a more stable place for them. So let's draw a little comparison there here, just to let me make some room here. And I'll draw 2 different cations. Let's think about these 2 cations momentarily and try to imagine which of these 2 cations is more reactive. I just gave you enough information to answer this question. You probably have an idea for which of these types of cations is more reactive, or maybe you don't. But I just told you, in essence, how to answer this question. So I've got 2 different cations, and the way to answer this question is we finish this up by drawing the fact that there's an empty p orbital on carbon, centered on carbon here. And here there's an empty p orbital located on nitrogen. Let me draw it in. It's empty. It would love to have a pair of electrons there. And what we need to do is think about the effect of electronegativity on the energy of atomic orbitals, and all orbitals associated with that nitrogen atom. So the effect of electronegativity is that all of these energy levels will drop. If I were an electron, I would much rather be on one of the p orbitals on nitrogen than on one of the p orbitals on carbon. The effect of electronegativity is that these p orbitals will be lower in energy. The effect of electronegativity on the s orbitals is that they will be lower in energy on nitrogen. And that makes sense. Let me sketch out the periodic table for you just in miniature form. As we march across the periodic table from boron to carbon to nitrogen to oxygen to fluorine, things become more electronegative because there are more protons in the nucleus. There is one more proton in the nucleus of carbon. There's yet one more proton in the nucleus of nitrogen. There's one more proton in the nucleus of oxygen. Those protons have a positive charge, and if you were an electron, you would enjoy those positive charges more. So this makes total sense that as we go to more and more electronegative atoms, that we should expect all the orbital energies to decrease if they are involved with that nitrogen atom. So that's a powerful idea. So you can guess from this that this empty p orbital is more reactive, more electrophilic than the empty p orbital that I drew on that carbocation. Just based on electronegativity, and we represent that with that orbital energy diagram. So a very powerful idea to extend. Okay, so let's talk about hybrid atomic orbitals. We're done talking about just plain simple atomic orbitals, s, p, d, and f. And let's talk about what happens as we mix together different atomic orbitals. Okay, so I'm going to give you a rule for mixing orbitals, for thinking about the way that orbitals mix together. It's best to think of them as mixing two at a time. And the rule is pretty simple. If you mix two orbitals, you get two orbitals out. I take two orbitals and I mix them together, and there's two different ways that they can combine together. And this is a result of that phasing idea. There's two different phasing combinations for every orbital. When you mix them together, there's two possible ways that they can interact based on phasing. So let me start off by drawing out just an atomic orbital energy diagram. Once again, I'm basically repeating what I showed you before. And I've got this sort of arbitrary axis. It used to really bother me when I was a graduate student. It's like, why don't they draw units on there? The units are actually in electron volts. If you'd like, you can convert those into kcals per mole, but it won't do you any good. The only thing energies in kcals per mole are good for are converting into number ratios. 10 to 1, 30 to 1, 0 to something. That's the only thing kcal energies are good for. And we're never going to do that with orbitals. We're never going to divide into ratios. This orbital is 99% more populated than the other one. So don't worry about the fact that there's no energies on this axis. Again, they're measured in electron volts typically. And you don't need to worry about that. So I'm going to start off by drawing out the orbitals. This could be on a second row atom, and it could be carbon, nitrogen, oxygen, doesn't matter. And those are the orbitals that matter are the 2s orbitals and the 2p orbitals. There's a 1s orbital that's way down below the level of the floor. That's never going to be involved in bonding. Don't worry about that. So I'm going to start to soon abbreviate like I did over here, was just writing p and s. But you just have to remember that's the 2s and the 2p orbitals that are important for second row atoms like carbon, boron, nitrogen, oxygen. So if I represent these orbitals, let me once again draw out these canonical orbital shapes. And the phasing is arbitrary here. So one is aligned with the x-axis. We would call that the p sub x orbital. Sorry, y-axis. One is aligned with the z-axis coming straight out of the board. That would be the p sub z orbital, etc. And the s orbital we would draw as sort of this sphere. Actually, the 2s orbital has this egg-yolk inner core that has the opposite phasing. But I never represent that inner core. I just draw a circle. And that's good enough for us. There's 2 arbitrary phasing combinations to that. What I want to do is I want to think about the fact that in order to get ready for bonding, we can think about this in a different way. We can take exactly that same carbon atom, if this is carbon, and we can think about a different set of 4 orbitals by mixing orbitals together. And we're going to call this hybridization. When we mix orbitals on just a single atom, we're not forming bonds, I'm just talking about a single carbon atom, I have a different way of thinking about this carbon atom, for example. And what I can do is I can think about, just invent little games like what would happen if I mixed this 2s orbital with this 2p orbital. If I take a low energy orbital like the 2s orbital and I mix it with a high energy orbital like the 2p orbital, on average I ought to get 2 orbitals out because I mixed 2 orbitals, and they ought to be somewhere right in between. And that's exactly the picture that we get. So let's imagine that I take this orbital here, the py orbital, and I mix that together with let me call that the px orbital. That looks like an x-axis. If I take the px orbital and I mix that with the 2s orbital, what I should expect is these other 2 orbitals will stay at the same energy. I'm not talking about mixing those. But I should get 2 new orbitals out. And they should be halfway in between the high energy and the low energy. So I'll try to draw my new orbital energy lines here. And here's my 2 hybrid atomic orbitals. It's just a different way to think about this carbon atom. I'm not changing the carbon atom in any way. And so what I get out of this are 2 non-bonding orbitals. I mean, if I draw them that way, 2 new orbitals that are ready to form bonds. And the hybridization of those orbitals is not s, it's not p, it's 50% s and 50% p. And we represent that with this sp sort of symbolism here. So a carbon atom normally has 4 electrons ready for bonding. So now I would have 1 electron in each of these orbitals and 1 electron in each of these p orbitals ready for bonding. And so you know this to be the hybridization, I hope, for something like an alkyne. Those 2 bonds sticking out at the sides are the result of these hybridized orbitals, these sp hybridized orbitals. And then of course you have room for pi bonds. Let me try to draw these in sort of a bluish color. And then we have room for pi bonds if we wanted to form an alkyne like this. That's what the p orbitals would do. We'll talk about that deconstruction in just a second. The point is that we can take the atomic orbitals and we can think about hybridizing them with each other. So let's go ahead and look at another hybridization combination. There's other ways that we can hybridize these, and I hope you're familiar with these. So let's suppose I take one of these orbitals and I mix it with those others. I'll be left with one of the p orbitals, but I still have 3 other orbitals left. And now these orbitals, if I mix 2 of these p orbitals with one of the s orbitals, I'll have 3 more orbitals. And now with that extra p orbital mixed in, the average energy ought to go up. And these are sp2 hybridized orbitals. I can draw these with a little non-bonding symbolism there. We'll talk more about that in just a bit. And hopefully you know that whenever you have trigonal carbon, these are the orbitals that are forming those bonds. They have this hybridization associated with them that's sp2. Finally, I'm going to try to move to the other board here. I'll draw the last possible hybridization combination. And I shouldn't say last possible. These are kind of extremes. But if we understand these extremes, then we can understand things that are in between. And then finally, the last possible combination is to take these 3 orbitals and mix them with this last p orbital to add even more p character. And so this is supposed to be on the same axis. And hopefully you know that this is sp3 hybridized. 3 parts p character, 1 part s character. That's the recipe. And I'll use a little non-bonding orbital combination. So those would look something like this. This is supposed to be a tetrahedral carbon atom with 4 sp3 hybridized orbitals ready for bonding. What's the really important point here? The really important point is that whenever you see orbitals that are higher in energy, they're more nucleophilic. If I were an electron in a higher energy orbital, I would be more nucleophilic. If you're adding to an empty orbital and it's lower in energy, you're more electrophilic. Hybridization tells you about chemical reactivity. It tells you about where to start your arrows. When you do arrow pushing, it tells you where to end your arrows. So last important point. Let me keep this on the board so it's at the same level. Has to do with the strict correlation between hybridization and geometry. Atom geometry correlates with hybridization. And it's maybe correlates isn't strong enough word. It equates with hybridization. So if I were to take a nitrogen atom, if I were super small, and I could reduce myself to the atomic level, and I could grab onto these bonds on ammonia or an amine and stretch them upward so that this were a planar molecule, what would happen is the hybridization would have to change in response to that geometry. If I placed this amine functional group into some molecule that constrained it so it had to be planar, that lone pair would become screaming hot in terms of nucleophilicity. Because by changing the geometry, I would be changing from an sp3 hybridized orbital to one that's purely p hybridized. And I just told you what the difference is between something that's sp3 versus something that's p. sp3 orbitals are lower in energy than p orbitals. Let me try to draw all these on a single diagram so that you can see what's going on. So if I have an s orbital down here and a p orbital up here, sp3 orbitals are lower in energy and p orbitals are higher in energy. sp orbitals are midway in between, and sp2 orbitals are up here. And you may look at this diagram, this pathetic diagram, and say, oh, but that energy difference is so small. The energy difference between a pair of sp3 hybridized electrons over there and a pair of p hybridized electrons is massive. The difference is massive in terms of nucleophilicity. And I'll put some quantitative numbers on that in just a little bit. But you need to appreciate this difference in reactivity just by changing the geometry. It's not sufficient to say that that's a lone pair on nitrogen. We have to go beyond that to hybridization. Okay, so hybridization is super important. Understanding the hybridization of every atom and every molecule is essential. Okay, this is a command for you. It's a command that you must do this. Every time you see a molecule, I want you to deconstruct that into atomic orbitals. And I'm going to start with a very simple example so we can see how that works. I'll take hydrocyanic acid. And let's try to think about the atomic orbitals, about a picture of bonding that's based on hybrid atomic orbitals. How do I think about what kinds of hybrid atomic orbitals would make a bond between nitrogen and carbon? A sigma bond or a pi bond? So the way I think about that is, let me just draw the three atoms here without the bonds, and let's try to draw some hybrid atomic orbitals associated with that. Okay, what's the hybridization of the carbon atom here? It's sp hybridized. And you know that because this is a linear molecule. I told you that geometry correlates with hybridization. If it's linear, that means there's two p orbitals that never mixed in. So I'll try to draw one p orbital that's on the y-axis and another one coming out at us. This is supposed to be aligned with the z-axis coming out of the board, but I'm not very good at drawing that. What's the hybridization of the nitrogen atom? It's sp also. And so again, I'll try to draw one of the p orbitals coming out of the board. And I'm going to label this p orbital on carbon, p orbital on carbon. I'll put a little subscript c there just so that I don't forget that that's a p orbital on a carbon atom. And as we just said, a p orbital on a carbon atom is not the same as a p orbital on a nitrogen atom. P orbitals on nitrogen atoms are lower in energy. And that's how you get those pi bonds. 2 of the 3 bonds here are pi bonds that result from the mixing of those p orbitals. Okay, last we're going to draw on the hybrid atomic orbitals. And I'll change this line here to blue just so I can more easily see it. And I'll remember that there's an sp2 orbital sticking out this side. And I'll hybridize it in this way. And there's a tiny lobe on the back end. And then for the nitrogen atom, there's another sp2 orbital that's sticking out. And these two are combining together to make that carbon-nitrogen sigma bond. And there's a little orbital on the back end sticking out. Okay, I've got 3 orbitals now. Let me go ahead and label these. This is my sp2 hybrid atomic orbital. I'll call this sp2. And I'll say that it's on carbon. And then this one here, I'll put a little label line, sp2 on nitrogen. And those 2 hybrid atomic orbitals get together to make a sigma bond, the blue sigma bond in my Lewis structure. Okay, there's a lone pair in an orbital that's sticking out here. Let me draw that. And that's sticking in another sp2 orbital with its lobe on the back end. And I can phase it this way if I want. Let me not phase that part. And I'll call that another sp2 orbital on nitrogen. And I need to do the same sp. Thank you, everybody who got upset by that. These are sp hybridized. That's what we said before. Sorry, I'm getting p orbital happy here. So these are sp hybridized. We said carbon is sp hybridized, nitrogen is sp hybridized. So these are sp orbitals on nitrogen. I need to do the same thing for that carbon atom and draw another bond going back here. So let me draw another sp orbital on carbon sticking out on the back end. And then finally, that makes a bond with hydrogen. Hydrogen only has a 1s orbital to contribute. We don't need to worry at all. There is no way to do hybridization with a hydrogen atom. It's only got 1 orbital. It can't hybridize with its own atomic orbitals. And it's the combination of this 1s orbital and the sp orbital that makes the bond. Now, why am I so intensely interested in the hybridization of these individual atoms? Why am I so intensely interested in the hybridization of this bond? Why am I so intensely interested in the hybridization of this lone pair? What I'm trying to do is I'm trying to gauge how much p character there is in that bond and in that lone pair. And you should be asking yourself this every single time. This is the fundamental question that you need to ask for every single structure you draw, for every single bond, for every single lone pair. How much p character? Let me just remind you of why I'm always asking myself how much p character there is. It's because p orbitals are high in energy, and the more p character you have, the more nucleophilic you are. I am always asking myself how much p character there is in every single bond and every single lone pair. Because I care how nucleophilic this bond is, I care how nucleophilic that lone pair is relative to other molecules. Now let's put some numbers on this. I keep telling you it's important to think about p character. Let's put some numbers on how important it is to think about p character. So the fundamental idea is that the more p character, the more reactive. I'm going to start off by looking at nitrogen lone pairs because it's easy to rank the reactivity based on pKa, or acidity. So I'm going to draw a little table here. And in my table, I want to compare lone pairs on nitrogen. So if I had some alkylamine with a carbon bonded to an NH2 group, there's a lone pair on there. If I have some sort of an imine with a lone pair on nitrogen that has two other bonds to it, that's not the same. And if finally I compare that to that hydrocyanic acid or to an organic nitrile, I would end up with something that looks like this. So here's three different nitrogen lone pairs. They're all lone pairs. They're all on nitrogen, but they're different. So I want to start off by ranking the hybridization. What's the hybridization of this lone pair on the top nitrogen? It's sp3. How about the second one? The imine, or pyridine, or imidazole. And then finally I get down to the nitrile, and we already said that that's sp hybridized. Now, what's the percentage of p character in this top case, sp3? 75% p character. sp2, what's the percentage of p character? About? It's about 2/3 or 67%. And then finally the sp, 50%. These are paltry differences. 75 cents, 66 cents. What's the difference there, right? How big of a difference could that make? Maybe you already know something about the relative basicity of these. I can go to a pKa table and look up the converse of basicity, acidity. What you find out is, I'll assign this a relative value of 1, that an sp3 hybridized nitrogen lone pair is 100,000 times more basic than an sp2 hybridized nitrogen lone pair. You know, if you put $1 in front of me and $100,000, I would have no problem seeing the difference between the two piles of money. It would be totally trivial. And yet, why is it so hard to see the difference between these two? The difference is just as great, 100,000 times in reactivity. So when I come over to this other board here, let me raise this up and pick a new board. And I draw out these two molecules. Which of these is more nucleophilic? Now the answer should be instantaneous. This one is more nucleophilic. It is about 100,000 times more nucleophilic than pyridine. Lone pair on nitrogen, but they're not all the same. And that's because this is sp3 hybridized and this is sp2 hybridized. Those lone pairs are totally different. Now if I come down to an sp hybridized, okay, this is like a difference of what? I'm not good at math. 8% versus 17%. How big of a difference could that make? How many zeros does it matter how many zeros I drew, really? It's 15 zeros, or 10 to the minus 15. There's a huge difference in reactivity. This is the effect of p character. What looks to you like small differences in p character translate into phenomenal differences in orbital energies. And this is why, if you, from the very beginning of sophomore organic chemistry, were not paying attention to p character, I don't know how you made sense of the subject. They probably told you this at the beginning of the book and at the beginning of the first quarter, and then they forgot to emphasize how important this is. So I'm going to ask you to pay attention to hybridization from now until the end of your career as organic chemists. Let's make sure we understand these differences. Which of these oxygens is more, I guess what I'm asking is basic. Which of these oxygen atoms would you expect to be more basic? I've got a ketone and an ether. Yeah, the ether oxygen. They both have two lone pairs, but these lone pairs are sp2 hybridized, and the lone pairs sticking off of this oxygen are sp3 hybridized. Now the important point is we look at a pKa table, and the difference is not 10 to the 5th this time. It's not always 10 to the 5th. Here it's only 1,000 times more basic. But again, when you're pushing arrows, If you know that one lone pair is 1,000 times more reactive than another, that kind of settles the issue. It doesn't have to be 100,000 times. Even 1,000 times more reactive is useful to you in terms of thinking about reactivity. This is incredibly powerful stuff. But let me put one sort of fly in the ointment here, one word of caution in applying this very simple idea that hybridization is important and that p character correlates with basicity and nucleophilicity. More p character means more nucleophilic and more basic. I've got two oxygen atoms here. I've got a carbonyl oxygen on top and a carboxyl oxygen on the bottom. Top and bottom, which oxygen atom is more basic? The top one. We mentioned this yesterday in discussion section. The top atom is more basic. I don't know of a single example ever in the field of recorded organic chemistry where the bottom oxygen atom acts as a nucleophile or as a proton acceptor. Now, why is that? The only way to understand that is by truly understanding the structure and geometry of this molecule. In order to understand the geometry and the hybridization, we need to remember that there's resonance. And resonance is going to influence our picture because it tells us about the hybridization. The true structure of this molecule really has partial double bond character between this carboxyl oxygen and the carbonyl oxygen. Once we draw a resonance structure for this, we realize that these lone pairs up here are not really sp2. And this lone pair that I've got drawn at the bottom is not sp3. You can't think about the hybridization of these atoms until you've drawn the resonance structure. So you have to incorporate resonance before you assign the hybridization to something. So really, this is more like sp3 in this extreme resonance structure, and this is more like sp2. And if you draw the charges, it's even less likely you would ever in your life make the mistake of trying to protonate this oxygen atom on the bottom. Who would do that? Nobody. Nobody would make that mistake. So you have to think about resonance before you try to assign hybridization. And as soon as you draw the resonance structure, it's absolutely clear that this is the more reactive set of electrons on the top oxygen. There's no cases where the carboxyl oxygen on the bottom is more reactive. Okay, so we've talked about atomic orbitals. We've talked about hybrid atomic orbitals. We've talked about the supreme importance of p character. P orbitals are higher in energy. More p character means more nucleophilic. Let's go ahead and talk about mixing hybrid orbitals in order to generate molecular orbitals. So again, the intent was that this is supposed to be review. I'm stunned. I went back and I looked at the sophomore organic chemistry text that I teach out of, and all this stuff is in there. But somehow it just gets lost and dropped. All of these important concepts get lost once you get to the chapters beyond chapter 1. Okay, so let's go ahead and build up this picture of starting with a carbon atom that has atomic orbitals on it. So let me go ahead and depict the atomic orbitals on carbon. There's a 2s orbital that's shaped something like this. And I'm not going to worry about the phasing. There's this egg yolk shaped part of the orbital that's in the center. I'm not even going to draw that because it will make the picture too confusing. Inside here, I'm going to draw the picture of a 2x orbital, or sorry, a px orbital. There's a p orbital. I'm kind of overlaying it on top. It looks a little bit confusing. The actual overall shape of a p orbital it fits inside a sphere. So ChemDraw draws these orbital shapes that are so badly distorted you'd never know what a real p orbital looks like. So we take two atomic orbitals. Let's suppose we had a carbon atom and we wanted to get that ready for bonding. What we think about is the mixing of the p orbital here with the s orbital here, two s orbital and a 2p orbital, and we think about the idea that that can hybridize. So we've just been through this, but now I'm not drawing out the energy diagrams. I'm just drawing pictorially the way I think about this. Yeah, an s orbital and a p orbital can get together to make two different sp type orbitals. So here's one of the two sp orbitals. I'm going to draw this particular one with that phasing combination. And I can imagine this interacting with another atom to make a bond. So this is my hybrid orbital here. And I'll draw that interacting with a hydrogen atom. And I'll make sure the phasing combination matters. If I want to represent the formation of a bond, I have to make sure that the phasing, the arbitrary phasing, either hashed or unhashed, matches the phasing of this orbital. If they don't match, then it's an antibond. It's the opposite of a bond. And when I mix these two orbitals together, when I mix this 1s orbital on hydrogen with this hybridized sp2 orbital on carbon, sorry, sp orbital on carbon, I get a new bond. And that's a sigma bond. And it has a shape that looks something like this. Let me try to get this right. And if I wanted to give you extra information, I often put subscripts on my orbitals to give you extra information. That's not just a sigma bond. It's a sigma bond between a carbon and a hydrogen atom. And that's different from a sigma bond on a nitrogen and a hydrogen atom. Orbitals on nitrogen are lower in energy and less nucleophilic. CH bonds are higher in energy and more nucleophilic. So this is a molecular orbital. And you should already be familiar with this nomenclature. Double and triple bonds we call pi bonds. Single bonds we call sigma bonds. You should be familiar with that kind of idea. So I want to return to this, the way we started our class. We started our class by talking about arrow pushing and the idea that we're going to use arrow pushing to help describe one part of a powerful equation for thinking about reactivity. So remember I started off by telling you that any time two things get closer and closer together, if we wanted to think about the interaction between those, the energy we get, either forming a bond or sterically bumping into each other, we have this equation that we use to think about the energetic consequences. We said that this equation obligates us, whenever we have two things interacting with each other, obligates us to add together all the charges. So if I had some sort of an amine interacting with some sort of an electrophilic organic compound, like bromomethane, as these get closer and closer together, if I want to calculate how good or bad it is for these things to get closer and closer, I have to think about the charges between the proton and the bromine, the proton and the carbon, the proton and the H. I have to think about the charges on the nitrogen interacting with the proton. You have to add that up for every single atom in your system if you want to get a full accounting for the overall charge effects as these things come closer together. We have to think about the non-bonding interactions, the steric interactions that don't form bonds. The bumping of this H into that H, the bumping of this nitrogen into that H. In addition to thinking about the formation of a new bond, we have to think about all those bumping interactions that aren't good. And we add all of them together as these get closer and closer together. And then finally, this is our arrow pushing. We agreed that lastly, arrow pushing wasn't going to represent sterics, it wasn't going to represent charge, it was going to represent the interaction of this filled orbital, this sp3 hybridized orbital on nitrogen, with some sort of an antibonding orbital that we usually don't draw. with Lewis structures. Now I want to get down to the nitty-gritty of this equation because I didn't tell you the form of this equation. And now I'm going to have to give you an equation that may look sort of complex, but it's not too complex. That's the equation. This is the equation that underlies arrow pushing. It says, what does this equation tell you? That if you want to think about how good your arrow pushing is that good arrow pushing or bad, or is that likely or unlikely? Was that a good idea for me to push arrows like this? You have to think about the interaction spatially of the orbitals. Are they getting close? Are they overlapping in space? How good is that degree of overlap? And then secondly, you have to think about the difference in energy between the orbitals. Is this high in energy? And is this empty orbital low in energy? And it is the difference between the filled orbital energy and the empty orbital energy that determines how much energy you get as these get closer and closer. So let's take a look at that. And I want to start off by using something called a molecular orbital interaction diagram. It's a device that you should have been introduced to back in freshman chemistry, and then you never used it again. It was like, why did we learn that? I have no idea why we learned these molecular orbital interaction diagrams. So let me just start off by reviewing pictorially the molecular orbitals in a molecule. If I were to draw an energy diagram showing the molecular orbitals of ammonia, for example, what would it look like at the level of resolution that I think? And again, don't worry about the energy on the energy axis. The big point I want to make is you got all these molecular orbitals associated with any molecule. And when you look at the electron occupation, it looks something like this. There's filled orbitals that have 2 electrons in each, and then above that there's empty orbitals, and they're not all mixed together. And always, these empty orbitals, and I'll call them molecular orbitals, MOs, the empty orbitals are always higher in energy than the filled orbitals. It's just a fundamental fact. If I measure the energy difference between filled and empty, there's always some sort of an energy difference associated with them. Okay, so we're going to learn about how to think about the interaction of one molecule here that has energy levels with another molecule that has its own molecular orbitals that are different, and how to think about the differences in energy in those orbitals. And instead of thinking about an actual chemical reaction, what I want to do is I want to draw a picture of some sort of a species. And I want to ask you, what do you think is the geometry of this species? It's a carbocation. Or is it a carbocation? What does this look like? I think that's stabilized, and I think you can tell that it's stabilized. But how do you think about the stabilization? Is this like an allocation? That has this sort of allylic resonance? If so, that would mean the positive charge is distributed on both of these carbon atoms. But the alternative way of thinking about this is maybe the lone pairs donate into that, and maybe it really looks like this linear molecule that might be best represented like this. And what kinds of tools do you have at your disposal to answer a question like that? They are exactly the same tools that you use to think about this reaction between 2 molecules. And the difference is here we're talking about 2 kinds of nucleophiles, a pi bond versus a lone pair that are attached to the same nitrogen atom. It's just the same story. Here I'm talking about a nucleophile on 2 different molecules, and here I'm talking about 2 different nucleophiles that are on the same atom. So I'm going to start off by drawing a molecular orbital interaction diagram that will immediately answer that question. And here's what a molecular orbital interaction diagram says. I've got some nucleophile with a filled orbital. I've got some electrophile with an empty orbital. So I'm going to start off by representing the case where the lone pair on nitrogen is interacting, or sorry, the pi bond on nitrogen, the double bond is interacting, so that bond between carbon and nitrogen, the pi bond, if it's donating into the carbocation, I need to draw that as my nucleophilic filled orbital. Then on the other atom, the carbon atom, I've got some empty orbital. This empty p orbital, the carbocation orbital on the carbon atom. And I have to think about the interaction of these two orbitals. When I mix two orbitals together, when I donate the electrons from that carbon-nitrogen pi bond into the carbocation, when this donates into that, I have to get two new orbitals out. Here's the orbitals in my product. When I mix two orbitals, I get two orbitals out. When I mix a filled orbital with an empty orbital, when I donate these electrons in, I'm going to get two orbitals back out. So here's what the orbitals would look like in my product. One is going to be lower in energy, and one is going to be higher in energy. And if I try to diagram, I'm going to try to draw this sort of edge on so you can see what I'm talking about. I'm going to have some empty orbital here on the carbon atom. That's an empty orbital on p carbon. And then there's this pi bond, and I don't know how good of a job I can do to represent this pi bond here, but I'll try to smear some electron density and make that my pi bond. This is the pi bond between the other carbon-nitrogen. So what happens when those two orbitals overlap? What happens when this pi bond between carbon and nitrogen donates into the carbocation there? I'll get two new orbitals out, and this one is going to have pi symmetry, the new orbital that I get out. And this is if they're in the correct phasing combination where the top is hashed and the top is hashed, but there's also an anti-phasing combination to the way those two can combine. And when I mix the other phasing combination, I'll get an anti-bonding orbital. We represent that with a star that's just as destabilized as the new bonding combination was stabilized. So I'll generate some new pi bond if I think about that interaction. Now let me contrast that, and I'm going to try to quickly draw out this diagram because we're running out of time here. Let me contrast that with an alternative scenario. And that's the lone pair interacting. And I'm going to try to draw my diagram with the same axis. I didn't label it over here. And I'm trying to make sure I draw my p orbital at exactly the same energy, because that's not different. The carbocation is the same. But instead of thinking about the pi bond interacting with that orbital, I'm going to think about the lone pair on nitrogen interacting. And what I immediately need to do is think about the idea that non-bonding lone pairs on nitrogen, sp2 hybridized non-bonding lone pairs on nitrogen, are higher in energy than pi orbitals. And this is something that we will talk about shortly. I'll tell you how we know that shortly in our next lecture. And if this is higher in energy, I'm going to try to draw a line across here just to show you that I'm trying to draw this non-bonding lone pair on nitrogen being higher in energy. If this is higher in energy, then the difference between these two is smaller. And if the difference between those two is smaller, I've lost my equation here. That equation that I showed you, if the difference in energy is smaller, the overall interaction energy is bigger. In other words, you want more nucleophilic things that are higher in energy, and if these are closer in energy and the energy difference is smaller, the overall interaction energy drop is bigger. You get more interaction energy out. When these two are smaller. So this is delta E between our MOs, and I get more interaction energy out, E sub interaction. I get more interaction energy out than when these are far apart. And you kind of knew that. What I'm telling you here is, well, this is less nucleophilic. Of course it's harder to donate into that empty orbital. This is more nucleophilic. Of course it's better to donate into that empty orbital. You get more overall bonding energy out. What that tells you is the answer is it's the nitrogen lone pair that should want to donate into that cation. This should be a better representation of that structure because nitrogen lone pairs are more nucleophilic. Okay, sorry I went over on my time. We'll get back together on Friday and I'll tell you about how did I know that this nitrogen non-bonding lone pair would be more nucleophilic than a pi bond. Take you back to where we left off on Wednesday. On Wednesday we started talking about orbitals. We're going to spend the rest of this quarter using arrow pushing as a way to describe orbital interaction. So we really need to be comfortable with these three types of orbitals: atomic orbitals, hybrid atomic orbitals, and molecular orbitals. And really the rest of this quarter is going to be molecular orbitals. So I introduced you to this idea of a molecular orbital interaction diagram that allows us to graphically depict something we don't see when we draw Lewis structures. What we don't see when we draw Lewis structures is the energies of the electrons that are attacking. That's what we don't see. And so the molecular orbital interaction diagram is designed to show you graphically the energetic consequences of an interaction like this. Let's just imagine that water does an SN2 attack on chloromethane. The way to think about that is that my arrows represent the interaction of this filled orbital here, this non-bonding lone pair on oxygen. We can represent that with an N with a subscript O, attacking an antibonding orbital, donating its electrons into this antibonding orbital, and therefore breaking the bond. And I would depict that interaction like this. A filled orbital like this, non-bonding orbital on oxygen, is interacting with an unfilled orbital, this sigma star antibonding orbital for the carbon-chlorine bond. And if I mix two orbitals, I have to get two orbitals out. I get a filled orbital that's lower in energy and an unfilled orbital. I create a new bond, a new oxygen-carbon bond. I'm representing it like this. I create a new antibonding orbital with that goes along with that new bond that we create. Okay, so the important aspects of this diagram that we said that whenever the energy difference here is small, whenever nucleophiles are high in energy and energetic, whenever electrophiles are low in energy and easy to attack and easy to donate into, that results in a small interaction, a small difference in the orbitals of that are interacting, and that results in a very big energy benefit. You get a very big drop in energy for the new orbital that you create, and consequently your reactions will be exothermic and fast, and that's what we care about. We care about reactions that are fast. Okay, so that's the MO interaction diagram. And you may not be experienced using those, but sometimes I'm going to fall back on those to try to explain the energetic consequences of our arrow pushing. So let's continue talking about this idea that there's a way to depict things with MO diagrams. So we're going to talk about frontier orbitals, and I want you to consider another SN2 reaction. I'm kind of getting tired of these very simple reactions, but we have to start with things that are simple. And I want you to think about this idea that maybe ammonia could come close to bromomethane. Maybe something would happen as they interact with each other. And if you want to think about the interaction of an ammonia molecule with bromomethane, we have a rule that we have to satisfy, and that is that when two reactants approach, all of the filled orbital MOs in one molecule will interact with all the unfilled MOs in the other molecule, and vice versa. It's going to be this crazy, crazy way to think about things. If we really want to be accurate about what's happening as these two things approach, we have to think not about just this, but we have to think about every orbital interacting. Let me show you what that means in terms of equations. Remember on that first day I said, I'm going to give you an equation with three terms that involves electrostatics, that involves sterics, and some sort of mysterious MO interaction mathematical term that looked like this. And there's a summation symbol in there that says you have to add up all the interactions for all the MOs in order to accurately quantify this. What that means is I can't just think about this interaction with sigma star here. I also have to add up the energy I get by doing a deprotonation there and attacking that antibonding orbital. Simultaneously, as this lone pair gets closer and closer, it's also overlapping with that empty orbital. I also have to think about the electrons in this CH bond coming back and attacking. and doing a deprotonation. There's an antibonding orbital that's empty. There's a filled orbital. And you have to think about those interactions, and you have to add up every single interaction. It just gets crazy. If you want to be accurate about the interactions between filled orbitals and unfilled orbitals, you have to add all this stuff together. And so let me use an MO interaction diagram to depict this. What I want to do is I want to take an axis for energy, and I want to depict one of the reactants, the ammonia, and it's a whole series of filled and unfilled orbitals. I've got filled orbitals for the ammonia, and then unfilled orbitals, and I'm not going to draw all of them. We don't need to draw all of them. You could add up the electrons in the Lewis structure there and figure out how many filled orbitals I need. So I'm just going to draw some of them. And let me draw the MOs for the other reactant, the bromomethane. It's also going to have orbitals that are filled and unfilled. I see bonds in bromomethane, therefore I must have some sort of bonding type orbitals and some empty orbitals. So I'm not going to draw all of them. I just want to draw some of them so you can see how crazy this interaction diagram would be. I have to think about the overlap of this, for example, non-bonding orbital on nitrogen interacting with sigma star for the carbon-bromine bond. But I also have to think about this interacting with every single other orbital simultaneously. And so the number of interactions is massive. And we're not going to be any good at this. Now I want to come back to the form of this equation because there's something in here that greatly simplifies our lives. And that is the fact that the interactions here are dependent on the difference in energies. In other words, when I look at this, I can tell that one of these orbitals is higher in energy and more nucleophilic than the others. And because this energy difference is in the numerator, I will get less interaction energy if I take one of these lower energy orbitals, like this one down here, and try to interact it with one of these higher energy orbitals. None of these are as energetic and as good as this. And as a consequence of that, we can ignore this. And when I come over here and I look at the empty orbitals, none of these orbitals are as easy to add into as this sigma star, the lowest energy unoccupied orbital, so we can ignore those. And usually we're going to be good at identifying which ones of these is most nucleophilic and which ones is not, which ones are not. And so we're going to ignore these as well. We're going to end up, because this is in the numerator and is only our overall quantity is only big when the two orbitals that are interacting are close in energy, we're going to be able to reduce every single interaction like this into the interaction of one filled orbital and one unfilled orbital. And that's like this right here. It greatly simplifies our lives. Kenichi Fukui won the Nobel Prize in 1981 for recognizing that when the denominator is small, this term gets big. That's the Nobel Prize right there for frontier orbital theory. You could have won that if you had recognized that the mathematical consequences of that. What that means is that if we're interested in the interaction of filled orbitals with unfilled orbitals, then we can approximate and say we don't have to be exact. We just have to look at the orbital interaction with just the HOMO and the LUMO. And we don't need to think about all these other arrows, just the arrows that matter most. So that's what frontier orbital molecular theory is all about. Frontier molecular orbital theory says, in simple terms, just look at the HOMO and the LUMO. And so let me just write that down to remind you. So I'm going to stop using the term HOMO and LUMO for the rest of the quarter. I may throw it in every once in a while. From now on, I'm going to refer to those as the frontier orbitals. The energy frontiers, the lowest energy empty orbital, the highest energy filled orbitals, we're going to refer to as frontier orbitals. And so we're going to spend the rest of our time using arrow pushing to indicate these interactions that matter most. Very powerful stuff, even though it seems very simple. Okay, so let's go ahead and take a look at the canonical frontier orbitals. We care about, I'm trying to convince you to care about the energies of these orbitals. Which orbitals are high in energy? Which orbitals are low in energy? That's our surrogate for asking which electrons are nucleophilic, which electrons are not so nucleophilic, which things are easy to attack, and which things are not easy to attack. So for the rest of this quarter, we're going to talk about 6 canonical frontier molecular orbitals. Molecular orbitals can have bizarre shapes, bizarre three-dimensional shapes spread out over entire molecules. But when you look at the frontier orbitals and the shapes that they adopt, there's only 6 basic shapes to those frontier orbitals. And let me try to give you the energetic consequences here. I'm going to start off by drawing a p orbital, for example, on carbon. P orbitals are empty. That's like a carbocation, or an empty p orbital on a borane. If I take 2 p orbitals on carbon, I can mix them together to get pi bonds. One will be lower in energy, and one will be exactly the same amount higher in energy. So pi orbitals are filled. That's a pi bond. Relative to that p orbital, pi should be equally lower, and pi star this should be an antibonding orbital, should be equally higher. Now, if I take another orbital and I mix it in with these in order to get a sigma bond, those are the lowest energy orbitals of all, the lowest energy filled orbitals of all. I can also mix in some s character and get a non-bonding orbital. If you mix in s character, that's definitely lower in energy than a p orbital. Those are things like sp3 lone pairs, sp2 lone pairs. Lone pairs are the highest energy filled orbitals that we will ever talk about. 95% of the time when you push arrows, your first arrow will start with a lone pair, a non-bonding lone pair with a pair of electrons in one of these n-type orbitals. And then the highest energy unfilled orbital that we can talk about will be a sigma star orbital. Yeah, you have a question?
Yeah. Lone pairs instead of the sp3 hybridized, but why are they hybridized if they're not bonding?
Because the other orbitals have to hybridize in order to bond. So in other words, if I draw ammonia, this has a certain hybridization because the nitrogen needed to use a certain type of hybridization to form bonds with the other H's. If it didn't form any bonds with anything else and was just an individual nitrogen atom, your view of hybridization is totally arbitrary. It's only once things start to form bonds with particular geometries, that's when you can decide on the hybridization. Okay, so what do we have? We've got a total of 6 types of orbitals. We've got 3 filled orbitals, 3 types of unfilled orbitals. These are our canonical frontier orbitals. And we are going to spend the rest of the quarter talking about the interaction of these 3 filled orbitals with these 3 unfilled orbitals. There's only 9 possible combinations. I basically covered the entire class for you right here with this diagram. So how hard could this be? And what we'll find out is it's immensely difficult and very, very interesting to tease apart reactions into these combinations. So like I said, we're really interested in how high in energy our orbitals are, how reactive this pair of electrons is in this orbital, or how low in energy this antibonding orbital is. We care about what things make things high in energy or low in energy, make orbitals higher in energy and lower in energy. So what I want to do is I want to spend the rest of this section on frontier molecular orbitals talking about how does electronegativity perturb the energies of these orbitals? How does bond length perturb the energies of those orbitals? How does conjugation perturb the energies of those orbitals? Because if we can decide which molecular orbitals are high in energy, we know where to start our arrow pushing from. So let's go ahead and start to talk about those trends. I'm going to start off by talking about electronegativity, and we've already covered this. I talked about it in the context of atomic orbitals. So let me go ahead and explain what I mean by this. Molecular orbitals centered on more electronegative atoms are lower in energy. So for example, if I try to imagine a lone pair on carbon, and let's suppose it's a carbanion. I'll put a little minus there just to remind myself. I'm going to compare a bunch of anions. If you wanted to draw that out, you might draw something like this. It doesn't matter whether it's butyllithium or some butyl anion, or we're not going to worry about what the R groups are that are attached to the carbon. What would happen if I replaced that carbon atom with a nitrogen atom, with something more electronegative? As soon as I switch over to a nitrogen atom, I now have one more proton in the nucleus. Nitrogen has one more proton in the nucleus. If you were an electron, you would want to be on the nitrogen orbital. What you can expect is every single orbital that involves that nitrogen atom will now be lower in energy. And that includes the non-bonding orbital on nitrogen, the lone pair on nitrogen. You kind of already knew that nitrogen lone pairs are less nucleophilic and less basic than carbanion lone pairs. And if I switch to oxygen and have hydroxide or alkoxide, again, let me be generic there, I should expect that to be less nucleophilic and less energetic than the lone pair on nitrogen. As I keep going more and more electronegative, I'll continue to see every single orbital that involves that atom drop. And so finally I'll get down to fluorine, which has no bond, or fluoride anion that has nothing bonded to it. And I should expect that to be the least nucleophilic and least energetic of all. So I'm really telling you stuff you already knew. You had an intuition, I'm sure, before you walked into this class that fluoride anions are less nucleophilic than carbanions. You already knew this effect of electronegativity. I'm just trying to graph it for you in terms of molecular orbitals. So let's go ahead and compare, talk about the impact on antibonding orbitals. Let's think about this for a moment. Imagine a nucleophile attacking ethane in order to pop out some sort of a leaving group. How many of you like this arrow pushing? Probably very few. Well, the arrow pushing itself is fine, but as a reaction, that doesn't look very plausible to you. And why is that? Let's go ahead and sketch out what happens as we take a sigma star orbital, like this carbon-carbon one, and we graph that. What happens if I replace this atom here with something else? I'm interested in the antibonding orbital here versus some other atom. Your intuition already tells you what's going to happen to this sigma star orbital energy. If I replace this carbon atom right here with something that's more electronegative, like a nitrogen atom, you might think that that empty orbital is easier to add into. If I replace that carbon atom with an oxygen atom and become even more electronegative, then that orbital energy is lower and it's easier to donate into. And then finally we get to something like a fluorine anion or a fluorine group, and now you're starting to get to the point where maybe you can imagine popping out a fluoride anion. You may have had all kinds of reasonings or rationales for why it's better with fluorine. Like, oh, fluoride anion is more stable. No, that's completely wrong. The reason why you could potentially push out a fluoride but never a methyl is because the sigma star orbitals get lower in energy when you replace carbon with something that's more electronegative. It has nothing to do with the leaving group and that thermodynamic aspect to the reaction. So that's why. It's this effect of electronegativity on sigma star. That's why you can't do this, but you can do this when this is something, when X is something that's electronegative. Okay, so that's the effect of electronegativity. You knew this stuff already. You just didn't have some sort of MO diagram picture for why that is true. Let's look at the effect of bond lengths on orbital energies, on the energies of frontier orbitals. Let's go ahead and take a look at the effect of making bonds either longer or shorter. In this case, I'll look at the effect of making a bond longer. So I want to sketch out the frontier orbitals that I might associate with a carbon-fluorine bond. And I'll draw a sigma star orbital for that carbon-fluorine bond, really high in energy. And I'll draw the sigma bond really low in energy. Sigma orbital, that's filled. I mean, sigma star is always really high. And what I want to do is I want to imagine, if I look at the periodic table, let me sketch out the periodic table here. As I drop down this row from fluorine to chlorine to bromine to iodine, what's happening as I drop from the second row with fluorine to the third row with chlorine is that atoms get bigger and bonds get longer. Orbitals interact less effectively when they're farther away. When I go to a carbon-chlorine bond, what will happen, and I'll try to distort this and make that look really long, because that's the way I'd like you to remember that bond. When I go to a longer bond, the overlap between this carbon and chlorine is poorer, and so I get a weaker bond. And because that bond is weaker, it's easier to break. This is the way to represent this graphically. Look at the effect of things being farther away. Poorer overlap makes weaker bonds, and those weaker bonds we represent like this. That means that that bond is more nucleophilic. If you ever have any reason to use the CF bond to attack something, you can assume that the carbon-chlorine bond will be faster to attack as a nucleophile. I'm not saying you'll ever do that. That's totally irrational. But if you had reason to, you could make this comparison. And as I keep dropping down the periodic table to larger and larger atoms, like carbon-bromine, the bonds get weaker. The electrons in that sigma bond become higher in energy. And the bond becomes easier to break. And finally, I'll get to a carbon-iodine bond. This is sigma star, sigma. I didn't intend to have stars here. Sorry, I'm going star happy. Those are the filled orbitals. Yeah, so these are all bonding orbitals. It's the antibonding orbitals that get the star. Now I'm going to make that look really long so you get a sense. I'm exaggerating how much of a difference there is in bond length. So this is the effect of bond length. As you go to longer and longer bonds, the bond itself becomes more nucleophilic, but it also becomes easier to break the bond. So if you ever wondered why it's so popular in organic chemistry to attack alkyl iodides, it has nothing to do with leaving groupability. If you learned some rationale that iodides are better, you totally learned something that was completely fictitious. This is why it's easier to attack alkyl iodides, because the sigma star orbital for that carbon-iodine bond is lower in energy because the bond is long. And you can take this bond length and apply it to anything you want. Longer bonds are more nucleophilic and less stable. Longer bonds are also easier to break. So let's extend this. Boron is a second row atom like carbon. Boron, carbon, nitrogen, oxygen, fluorine. Aluminum is a third row atom. Which of these do you think is more nucleophilic? These bonds are longer. These bonds are higher in energy. The aluminum hydride bonds are more nucleophilic. These bonds are way, 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 way more nucleophilic. You could have guessed that just by looking at the fact that aluminum is in the third row and boron is the second row. So again, for the same reason that alkyl iodides are more reactive than alkyl fluorides, these are better nucleophiles. This is a better and more reactive nucleophile. And I'll just write El plus for my electrophile. It could be a carbonyl. If you've ever worked with sodium borohydride or lithium aluminum hydride, you already know that tetrahydridoaluminate can burst into flames when you expose it to alcohols or to water. And borohydride will just dissolve and react more slowly.
So what about the non-bonded electrons on this?
There are no non-bonding electrons on these two in a correctly drawn Lewis structure. If there were, those would be the most reactive part. Okay, so let's go ahead and look at the effect of conjugation on our canonical frontier orbitals. I'd like for you, what you're going to find is very, very quickly, I'm not going to be drawing these MO diagrams anymore. Probably within a couple of lectures, you're not going to see them anymore. But I expect you to be using them to think about structures that you draw. We're going to be drawing large, hairy, complex molecules. And this is the kind of stuff you have to fall back on. Bond length, electronegativity, issues like that. So you notice there was this, when I drew it out, there was this pinching effect of the orbitals as I went to longer bonds. LUMOs got lower in energy, HOMOs got higher in energy. So we're going to see the same effect as we add conjugation to molecules. And what I wanted to do is I want to try to sketch out the pi orbitals for ethylene. There I go with the star again. Okay, so the filled orbital for this pi bond in ethylene, there's a filled orbital. That's the pi bond that you can see, that second bond. And then there's the antibonding pi orbital, and that you don't see. We don't draw those when we draw Lewis structures. And so what would happen if I conjugate that double bond to another CC pi system? What would happen is I would watch the filled orbital get higher in energy and the unfilled orbital get lower in energy. And as I keep increasing the conjugation, I'll keep seeing this effect increase. Pi will get higher in energy, pi star will get lower in energy. And this is all relative to a p orbital, the energy of just a plain p orbital. And you can continue this on ad infinitum, etc. And you'll see this pinching effect. So what's the implication of that? It's pretty profound. This is just like making bonds longer, this idea of pi conjugation. Let's go ahead and compare two molecules. Here's pentadiene. One of them is 1,3-pentadiene, and one of them is 1,4-pentadiene. And what I want to do is I want to think about these acting as nucleophiles. Maybe if I had some sort of a carbocation or an oxocarbenium ion, I could imagine this pi bond attacking to make a new carbon-carbon bond. We'll talk about those types of Prinz reactions or electrophilic aromatic substitution later. Which of these is faster? Conjugated or non-conjugated? Yeah, the conjugated one is faster. And the question is why? How could you have known that? I think in sophomore organic chemistry, we tell you something stupid like, oh, it makes an allocation and that's more stable. That's not the reason why it's faster. The reason why it's faster is over here. When you add conjugation, you raise the energy of the pi electrons. The HOMO in this, the pi electrons, are higher in energy than these pi electrons. That's why this is faster. Okay, now let's look at, I don't know if I'd call this the reverse, but it's almost the reverse. Let's think about something different. Let's think about a nucleophile attacking the pi system here. So here the conjugated system reacts faster with electrophiles. Which of these should react faster with a nucleophile? The conjugated or the non-conjugated? The conjugated should react faster. They both react faster. Nucleophiles and electrophiles react faster with conjugated systems. And again, in your introductory organic chemistry class, you probably made up some idea like, well, it makes a more stable allyl carbanion, or something that's just totally wrong. That's not why nucleophiles add faster. Nucleophiles add faster because pi star is lower in energy when you have conjugation. That's the effect of conjugation. It's just like longer bonds. And what's bizarre, and it's not bizarre, but I don't want you to get stuck in this conundrum here. Here's two molecules. They have the same molecular formula. These two molecules. The conjugated one is more stable. Conjugated molecules, molecules with conjugated pi systems, are more stable than comparable molecules that have no conjugation. How can it be that the more stable of these two molecules reacts faster with nucleophiles and faster with electrophiles? And it has to do with this diagram and what I'm not showing you. When I conjugate two pi bonds together, what I did not show you is that there's a bunch of other orbitals. There's actually two different pi orbitals. There's other sigma orbitals. Those get way lowered in energy when you conjugate. Overall, this whole molecule is more stable when it's conjugated than this one. But when I just look at the most reactive pair of electrons, and that's all I care about with this arrow pushing, the most reactive pair of electrons, I guess up here, is higher in energy, even though the molecule is overall stabilized. So it's possible to raise the HOMO in energy even while you're lowering all the other orbitals really lower. Don't confuse this pair of electrons that I'm showing with my arrow with the overall stability of the molecule. Those are two completely different things. These two electrons can become more reactive even though the overall molecule is more stable. And you need to separate those ideas. Okay, so that's all we have to say about orbitals for today, and we still have some time, so we're going to go on to the next topic. But again, I handed out a summary sheet for you that summarizes the effects of things like electronegativity on orbital energies. If those sheets are standing around, you can pass them around. Things like p character on orbital energies, things like bond length on orbital energies, effects of conjugation. And I expect you to be using these when you draw out structures. If you draw out a steroid or an alkaloid or some lithium enolate, you can extend these very simple concepts to very complex molecules. Okay, in the remaining time, we're going to start on the next topic, and that's going to be a discussion of energy. Yeah, so I was worried about that. Yeah, use the black pen. There we go. Okay, so the Gibbs equation. I think all of you are familiar with this kind of an equation. You learned it in freshman chemistry, G-Chem. You learned it in organic chemistry, and then you never use it again. And I want to boil this idea down to something very simple. I want you to imagine owing somebody some money. How much of these would you rather owe to somebody? It's not obvious. It's totally not obvious. I don't feel like it's obvious to me. I'm a pretty clever person. Let's imagine putting some gas in your tank. How many liters of gas does it take to fill your tank? Or even if I ask gallons. Does it matter whether I ask gallons? It doesn't matter whether I ask gallons or liters. You have no idea. You could, if you sat long enough, you could think about. The point I'm making is that logarithms and exponents are not intuitive. They're not intuitive. They're not intuitive to you. They're not intuitive to me. They're not intuitive to anybody but maybe a math genius like Ramanujan. It's not helpful for us to use numbers like this. And this is the problem with this equation. That's fundamentally the problem. So I'm going to ask you to not think like this because it's not intuitive. So let's talk about what is intuitive. And I'm going to encourage you to convert free energies into things that are intuitive. For the rest of your time as an organic chemist, I want to ask you to do this. Ratios are intuitive. And more importantly, base 10 ratios are intuitive to you. They're intuitive to you, to me. They are intuitive to my 4-year-old daughter. She can tell the difference between 1 and 10 and which is more. So I want to draw a table for you. I want to think about this. It doesn't matter what the actual molecules are. Any set of reactants and products where we think about an equilibrium. And I want to think about the impact of putting numbers, energies, into this equation over here that involves either natural logs or exponents. And what I want to do is I want to try to equate energies with numerical ratios. So let me make the table. So what I'll do is I'll draw out some sort of a delta G value. And then I'll go ahead and draw out the ratio of A to B whenever you have a free energy difference of some number between starting materials and products, or between two transition states. Doesn't matter. So I'm going to start off in the middle of this table. When delta G is 0 and the free energy difference is 0, what's the ratio of those two species at equilibrium when the free energy difference is 0? 1 to 1. And I have a very clear idea what 1 to 1 means. My daughter has a clear idea what 1 to 1 means. That's very easy to grasp. Now what's important is, what happens as I increase this A to B ratio from 1 to 10? I want you to know what that free energy difference is. And it turns out that that free energy difference is 1.4 kcals per mole. It favors the products in this case, so I'm going to put a negative sign there. I have no idea how to think about 1.4 kcals per mole, but I know how to think about 10 to 1. I know 10 is bigger than 1, and I know 10 is a lot bigger than 1. What's powerful here is that if the free energy difference is minus 2.8 kcals per mole, that the energy difference is now 1 to 100. And you get the trend here. I now expect you to know the trend. What happens if the equilibrium difference here is 1 to 1,000? What's the free energy difference? Minus 4.2. I usually can't even remember the 0.2. I'm like, oh, minus 4. But we'll put the 4.2 here. And I'm going to stop using kcals per mole. In this class, I always use sort of American kcals per mole instead of kilojoules per mole. OK, so every time from now on that I give you an energy difference, whether it's an energy difference between starting materials and reactants, whether it's an energy difference between two transition states, I expect you to convert that into a set of ratios in your mind because ratios are intuitive. Oh, this transition state is 1.4 kcals per mole lower in energy than this other one. That means it's 10 times faster. That's intuitive. If it's 4 kcals per mole, it's about 1,000 times faster. If the energy difference between starting materials and products is 1,000 to 1, you have a chance of getting over 99.9% yield in that reaction because the equilibrium will favor products over reactants. And we can go the other direction as well. If the energy difference is positive, 1.4 kcals per mole, now it goes the other way, 10 to 1 in favor of starting materials. You don't have a prayer of getting a good yield out of that reaction. Nothing you do can change that thermodynamic difference. And if I add another 4 kcals or 1.4 kcals per mole to that penalty, and so now that's really a disfavored reaction by 100 to 1, and you can keep filling. So I expect you to know that 1.4 kcals per mole is a factor of 10. And I expect you to apply that. So free energies are only useful to the extent that you can convert them to ratios. I expect you to be very fast with this 1.4 kcals per mole bit. OK, let me give you one more energy, or one more sort of rule to add on to that. Let me first by writing out the 1.4 rule. So 1.4 kcals per mole is equal to a factor of 10, either an equilibrium constant or in a rate constant. Yes? It's at 298. So, and I think on the problem set I ask you to do some conversion for a different temperature. OK. I'm not sure how to describe this. I'll call this the expert rule. Once you're really good at 1.4, you're really good at applying this and doing these factors of 10, I'll give you another rule. And that is that 0.4 kcals per mole is a factor of 2. These are the only ones I really remember. So if I see an energy difference in transition states that's only 0.4 kcals per mole, oh, this transition state is 0.4 kcals per mole in energy lower. Well, that means it's twice as fast. And I'm not really good with 0.4, so when I see 0.5, it's like, oh, that's about a factor of 2. That's kind of the level at which I think. So you'll have some chance to practice with that on the problem set. OK, so let's go ahead and let's talk about some real examples of this. If you're drawing this on a piece of paper, I advise you just to draw the cyclic ester, the lactone moiety there. That's all we really care about for right now. This turns out to be a clinically used drug. And there are some substituents on there, but that doesn't matter. And what I want you to think about is the reaction of this with water. So if you wanted to hydrolyze this open, in order to give this hydroxy acid, then what kind of yield can you expect for this reaction? I can tell you right now that the free energy change is this. And why would you want to hydrolyze that open? It turns out that if you don't, it's not soluble. It has very poor solubility. You can't administer this particular derivative of irinotecan as a drug. What's the yield? Very low. It's very low. At equilibrium, the ratio is going to be 1,000 to 1. That's 3 factors of 1.4. If it's uphill by 4.2 kcals per mole, you have no chance of doing this. In fact, there is a way to hydrolyze this. What you have to do is not use acid. You do it in base so that this side is not the OH but the carboxylate, and then it becomes thermodynamically favorable. That's what they administer as the drug in order to get solubility out of this. So you can't get better than a 0.1% yield if you're trying to isolate the free acid there. So let me go ahead and extend this idea that kcals per mole give us useful ratios to transition states. Let's suppose you do a lithium aluminum hydride reduction on this, and you get a 95% yield of the axial alcohol. And in case it's not obvious, there's the hydride group that I just added. This is what you get after workup. There's 2 possible transition states for this. And in one transition state, the hydride adds from the top. And in the other transition state, the hydride adds from the bottom to give you this product right here. And so what's the difference in energy for those 2 transition states, for axial attack versus equatorial attack? You can imagine the starting material going through one transition state or the other transition state. And the only thing you have, perhaps, is a TLC plate or some sort of isolated yield. How do you convert this into transition state free energies? What's the maximum amount of the other isomer that could have been obtained in this reaction? 5%. You already know 2 numbers in a ratio. I've got 2 numbers. I can make a ratio out of that. That means the ratio is at least 20 to 1. Right? I don't know how much of the minor isomer. Maybe it was 1%, but I know it was at least 20 to 1. It might be greater. And so what does that mean? It's a factor of 2, and it's a factor of 10 to 1. How much energy for a factor of 10? 1.4 kcals per mole. How much energy for a factor of 2? 0.4 kcals per mole. That means I know that the energy difference between this unfavored axial attack and the favored equatorial attack is at least, I don't know how much greater it is than 1.8, but at least I can give people a meaningful number. So every single time you look at a TLC plate and say, well, that spot looks about twice as big. Or you get a yield and you say, well, I got 60% of this isomer. I didn't get 40% of the other. You can create ratios. And when you can create ratios, you can create free energy differences. And it doesn't matter whether it's transition states or equilibrium values between starting material and product. And I encourage you to do that. Okay, we're going to come back and finish up these ideas of how to use energy. But I want you to practice this 1.4 kcals per mole. It's immensely useful, right? When you're discussing things with other chemists and you use numbers like this, it's not as powerful as when you use numbers like that.